Hi all, thank you for showing up. I'll be first presenting work by my lab mate Songduan Lee, which is joint work with his advisors Stephen Weber and John McLaren Walsh. His work is about computer-aided proofs for rate regions of independent distributed source coding problems. I take this opportunity to talk about high-level ideas in his thesis. So we all know that network coding outperforms routing for information transfer, and in such scenarios, we are interested in admissible source rate versus channel capacities trade-off. Furthermore, in storage, coding outperforms simple replications. And here we are interested in the trade-off between admissible source file size versus hard disk capacities. Both these type of problems can be mapped to a general model called multi-source multi-sync hyper-edge network. In this network, there are a collection of independent sources, and there are a bunch of intermediate nodes, and there are sinks that are demanding certain subsets of sources, and interconnections between the networks are all hyper edges because a same encoded message could be available to a collection of destinations. In such a network, we are interested in rate region or capacity region. Most importantly, we are interested in calculating it using a computer. And to this end, we made three major contributions. First one is teaching a computer to compute the rate region. Conventionally, you would sit down with a pen and paper and apply information inequalities one after another and try deriving the rate region, which takes a lot of time. On the other hand, with computer, you can solve thousands, millions, or even trillions of arbitrary networks using a computer all in parallel. So we want to see how many networks we can solve using our computational tool, and for that purpose, we developed enumeration algorithm. Conventionally, it is really almost impossible to list all the networks by hand due to large number of instances. With a computer, you can list billions or trillions of general networks and save time. Third contribution is about building hierarchy between the networks. So once we compute the network coding rate regions using our tool, we want to learn something from them. And for doing that, we develop relationships between the networks, especially the ones that correspond to sufficiency of linear codes. Furthermore, we are also developing relationships that enable one to combine networks with known rate regions and create a larger network whose rate region is also known. So for today, we will focus on a special class of networks, which is called independent distributed source coding problem, and it is abbreviated as IDSC, which we will soon define. The main contribution towards IDSC is enumeration of all the IDSC problems for a given size, and we use computational tool that we have to calculate rate regions for the enumerated IDSC networks. Here's the outline for today's talk. First, I'll talk about enumeration, and here we will first fix a network model and talk about minimality. So here's the IDSC network model. We have k independent sources which are available to all the encoders. Encoders output a hyperedge message which is available to a collection of decoders. And decoders, each decoder demands a certain subset of sources. Notation we use to specify the size of a given IDSC instance is k comma cardinality e, where there are k sources and cardinality e encoders. Overall, we have n equal to k plus cardinality e random variables. Next, we define the notion of minimality. In fact, we have 6 minimality constraints, which are all intended towards avoiding redundancy. So I'll give an example of one of the minimality constraints, which is sync minimality. If you see the example on left, the decoding ability of D2 for source Y2 is implied by decoding ability of D1 for source Y2. So in this case, we can simply delete Y2 from D2's decoding list and get this network. And in the enumeration, we'll label these two networks as same. Second, we define the notion of equivalence. This is mainly useful because we want to avoid networks whose rate regions can be computed from each other through some kind of permutation. First of all, we fix a representation for a network. Here we'll label sources as 1 to k and encoders as k plus 1 to k plus cardinality e. Since this is fixed for every IDSC instance of same size, the top part of the network is fixed for every IDSC instance of the same size. The only thing that makes a difference is the string definitions, which is given by this set W, which consists of IA pairs, where I is a source and A is a subset of encoders. This tuple basically means that source I is it is possible to decode source I from a collection of encoders A, and in this example, 2 is decodable from 3, 1 is decodable from 3, 4, and 2 is decodable from 4. And you can notice that one source can appear multiple times in W. So we'll collect all these things in W. Now we define equivalence using group action. The group that is acting is direct product of symmetric group of source labels and symmetric group of encoder labels. We are using direct product because we don't want sources to be permuted with encoders. This group acts on string definitions, which is W, by acting independently on I and A in each of the tuples in W. So you get a permuted version of W. And two networks are isomorphic or equivalent if they can be obtained from each other via label permutation. And in this example, these two networks can be obtained from each other by permutation of labels, which is 1, 2. Now we define something called canonical network or minimal representative from each orbit. If we take a specific network and its string definitions W and act on it with an entire group G, then we get something called orbit of that network. Networks in an orbit are isomorphic or equivalent to each other. We can also define something called transversal by collecting one representative in each orbit. And this representative is called canonical representative. And this representative is picked by using lexicographic order. And lexicographic order on tuples IA works in this manner. So IA is strictly greater than JA dash if I is strictly greater than J or I equal to J and A is strictly greater than A dash under lexicographic ordering. Once you have sorted the IA pairs inside a given W, then we can compare it to other Ws using again the lexicographic order. So here is an example of comparison of W and W dash, and W dash is lexicographically smaller than W because 1, 3 is lexicographically smaller than 1, 3, 4. While we are only interested in computing the non-isomorphic networks, we are also interested in how many isomorphs a given network has, and for that we can use orbit stabilizer theorem. Orbit stabilizer theorem gives size of the orbit of a given network, and which is equal to size of the group divided by the size of subgroup of it that stabilizes the given network. And in this example, size of the acting group is 2 into 2, 4. Size of the stabilizer subgroup is 2 because the only permutation that keeps the network invariant is permutation of 3 and 4 and identity, of course. And hence the size of the orbit of this network is 2, and these are the only two networks in this specific orbit. Once we have defined minimality and equivalence, we can go for the enumeration algorithm. Our enumeration algorithm is based on something called Leiter-Spiel, which computes transversal of orbits on size j subsets of subsets which we denote as pj of x, offset x, incrementally in j, and also gives symmetry groups and or stabilizers. So we will start with the transversal of pj minus 1, which is j minus 1 subsets of x, and transversal essentially contains all the canonical representatives, and Leiter-Spiel will extend each of these and compute canonical representatives from pj of x, and this can also be done while obeying certain inherited test function. Inherited test function basically means that if a set has certain property, then all its subsets also have certain property. And we will use this test function to encode some of the minimality constraints that are actually inherited. So for our network enumeration, the target is to enumerate all KE non-isomorphic IDSC instances and list, which is essentially meaning that list all possible Ws. And lighter speed will essentially add incrementally the decoders from 1 to no possible decoders. So the input set is set of all IA pairs. Acting group is the direct product that I mentioned before. We will test some of the minimality constraints in the algorithm, the extension process itself, and add decoders one by one. And we will stop when no new decoders could be added while still satisfying the inherited minimality constraints. And once every time we add new decoders, we will test the rest of the minimality constraints and output the instances that pass the other minimality constraints. And this way we obtain a list of non-isomorphic IDSC instances. So here's the result of enumeration. Cardinality M is a number of non-isomorphic networks that we listed using Leiter-Spiel algorithm. And cardinality M dash is a number of networks with isomorphism. And you could notice that non-isomorphic networks is a very small fraction of all networks. Here's a demonstration of all non-isomorphic 2-2 IDSC instances. So now that we are done with enumeration, we would like to actually compute rate regions. So first we'll look at formulation that we use for this computation. The rate region of a network is all possible rate and source entropy vectors satisfying all network constraints. We will collect the n network random variables and their adjoint entropies and define this set gamma n star, which is 2 raised to n minus 1 dimensional set, and it is a region of all valid entropy vectors, which we will soon define and revisit. The constraints on the network are L1, L3, L4 dash and L5. L1 corresponds to source independence, L3 corresponds to encoding functions, L4 dash corresponds to edge rates, whereas L5 corresponds to the decoding functions. Yan, Yang and Zhang gave an expression for network coding rate regions, which we use, but we have slightly modified it. This expression is in terms of gamma and star, and what we have modified is the constraints, edge rate constraints L4 dash, wherein we keep RE to be the variable. So we get directly a relationship between our edge rates and source entropies. So the main problem with this whole formulation is that gamma n star is unknown for n greater than or equal to 4. However, the trick is to use polyhedral inner and outer bounds on gamma n star. So the solution that we use is that we will substitute certain outer bound on gamma n star bar and get an outer bound on the rate region. We'll also substitute some inner bound on gamma n star bar and get an inner bound on the rate region. And if these two bounds match, we get the exact rate region. And the overall process can be written as take an initial polyhedron, add some constraints, and perform projection. And hence it becomes a problem of polyhedral computation. Furthermore, we define something called a notion of sufficiency. The outer bounds we'll be using is mostly Shannon outer bound, and the inner bounds are from representable matroids, which give scalar and vector bounds. So a notion of scalar sufficiency is that if exact rate region is characterized entirely by scalar codes over a certain field, then we call that network to be scalar sufficient. And if vector codes are required, we call that network to be vector sufficient. And the notation for vector codes here is that RVQ n dash is a rate region obtained by using codes that distribute n dash FQ symbols amongst n random variables. Here are the results for rate region computation. We computed rate regions for all IDSC instances up to size 3.3, and for all of these, simple binary codes suffice. and at most you require one extra bit. That is, the vector codes are also pretty simple as well. Furthermore, for each of them, Shannon outer bound is tight, and here's a tabular version of the result. So m is the number of non-isomorphic instances. Third column gives how many are scalar sufficient, and fourth column shows how many are vector sufficient. The computations for 3-4 IDC instances are still ongoing. Overall, in this paper, we developed an algorithm to enumerate networks up to a given size. And for all IDC problems up to 3-3, binary codes suffice and Shannon outer bound is tight. In future, we want to solve more IDC problems and get the smallest IDC networks where Shannon outer bound is not tight. Furthermore, we want to also combine the networks to get solvable large IDC networks. And all this discussion, along with network operations and results for general networks, you can check out Songduan's PhD dissertation. And this is the last reference in this list. Thank you.